Hello, this is Brett from SurvivalComms. Today we're going to talk a little bit about compasses. Land navigation, like radio, falls under the category of nerd sports, so it is well within our wheelhouse, I am proud to say. Analog land navigation is truly grid independent, but it is a perishable skill and has become so overshadowed by data-dependent GPS technology that it isn't seen as important or relevant in circles where it should be considered a requisite skill. As part of my personal crusade to help others help themselves, I purchased Christmas gifts for my friends that I feel they can use. I decided quality compasses would make a good gift and they should be part of any sort of kit. I found a great deal on new in the box Legacy Silva 25 Ranger compasses for 35 bucks each, and the seller had a bunch, so jackpot, my gift list just got shorter. So a week goes by and in my mailbox are the compasses. Open the package and haha, joke's on me. These are quadrant bearing compasses. Lesson learned, I shouldn't shop online after cocktail hour, yet here we are. So what is a quadrant bearing compass and how does it differ from a more conventional whole circle bearing compass? While you certainly can navigate with a quadrant bearing compass, interoperating with users of whole circle bearing compasses does present a challenge, and we will discuss how to accomplish this if you ever need to do so. Now, this isn't a land nav course, but we will be doing a tabletop exercise at the end where we put it all together, so let's get started. This is the face of a base plate compass with a whole circle bearing capsule. At this time, we're going to review the basic nomenclature and functions of the key components of a base plate compass. The first component we're going to discuss is the needle. The needle is attracted to magnetic north and serves as a reference for determining direction. The needle north is typically a contrasting color or shape on a base plate compass. Our next component is the box. The box is where we desire the needle to reside when determining direction. The position of the box is controlled by our next component, the bezel. Now, if the compass capsule does not have a box, you can box the needle by aligning it towards north on the bezel. The bezel is the ring which surrounds the compass capsule. Around the circumference are the graduations that allow us to determine direction. The whole circle bearing bezel has bearings that are marked around the circumference 360 degrees clockwise. 0 and 360 coincide with one another north, 90 degrees to the east, 180 degrees to the south, and 270 degrees to the west. Our grid lines are what we use as a reference between a map and the compass, maintaining a relationship with map north in route planning, etc. The forward index mark is where we read our forward bearing or azimuth, and this generally is our direction of travel or observation. The back index mark is where we read our back bearing or back azimuth. This forward and back azimuth is measured in degrees on our bezel and is the angular relationship between our box needle north reference and the direction of observation, travel, or plotting on a map aligned to a north reference. The mirror in its sighting line on the base plate compass allows us to observe the compass capsule and its relationship with the index marks, while observing fixed objects with relative accuracy. These objects may be ones we want a bearing of, or for the use of objects in our direction of travel that we are using as waypoints for land navigation. To take a bearing, simply find the object in the sight, then you box the needle by rotating the compass capsule and observe the bearing on the bezel's alignment with the forward index mark. Now that we have a basic understanding of a whole circle bearing base plate compass, we can study how the whole circle and quadrant bearing compasses differ and how to interoperate between the two. The quadrant bearing compass is used for land surveying and civil engineering purposes and is also known as a reduced bearing compass. The only difference in the two base plate compasses we are using today is in the bezel on the compass capsule. The operation is the same, we just have to do some math to interoperate in a whole circle bearing environment. The quadrant bearing compass gets its name as the graduations are 0 to 90 degrees per quadrant, and they're quadrant limited, as you can see here. The quadrants clockwise are northeast, southeast, southwest, and northwest. You can see the graduations for each quadrant do not always follow a clockwise rotation, and that is what makes a simple addition conversion difficult. Knowing the rotation isn't that difficult to remember, however, as saying northeast is clockwise while saying southeast is counterclockwise. Southwest is clockwise and northwest is counterclockwise. To convert the whole circle bearing, first, simply divide the hemispheres north and south. Our reference bearing in the south is 180, and the reference bearing is 360 in the northwestern quadrant. Now, the northeastern quadrant is 0, but it's a direct translation to whole circle bearing as it is clockwise to 90 degrees. So just think 0, no action necessary. And here's a simple calcs for converting quadrant bearing to full circle bearing in the northeastern quadrant. You're just going to go ahead and read it as it is. You're not going to do any addition or subtraction. The southeast, you're going to take 180 and subtract the observed quadrant bearing. And the southwest, you're going to take 180 and add the observed quadrant bearing. And in the northwest, you're going to take 360 and subtract the observed quadrant bearing. The next 4 slides are just simply applying these calculations to our 4 different quadrants. You can see it isn't too difficult to apply this conversion if required. In this particular example, when you were taking a bearing from an object, it may be confusing to ascertain the quadrant from your sighting on the fly from the mirror. In this case, simply draw a bead on the object, box your needle, confirm it, then lower the compass, copy the bearing, and convert it. Now let's move on to some practical exercises. This is the map we are going to use for the practical exercises. This will be a crash course on maps generated by Topo, which is free for you to use and generate your own maps, so feel free to geek out to your heart's content. This map represents a rural area of low elevation in east central Florida. This map covers an area approximately 6 kilometers long by 5 kilometers wide. At the bottom of the map is important information about the map, which we're going to discuss. Highlighted is the cardinal point showing map north and magnetic north. Magnetic north deviates from map north to greater and less extremes depending on distance from the agonic line, and this is known as magnetic deviation. This is something we will discuss in another video. In our next box, the highlighted information represents the map scale in kilometers. Below this highlighted is our map scale in U.S. statute miles. Below this highlighted is our representative fraction scale of 1 to 25,000, and this assists us in selecting the grid tool for the exercise. This highlighted box represents our map datum. The datum selected here is World Geodetic System of 1984, which is what GPS receivers normally default to. Matching datum between map and GPS is very important and should not be overlooked. This highlighted box shows our map grid format. The grid lines are oriented to map north, and the format we are using is United States National Grid. This is an easy-to-use format which will interoperate with military grid as well as UTM when the same datum is selected and the difference is understood. The practical applications shown today will work with any of these formats. The simplicity and practicality of grid in land navigation is well worth understanding. Highlighted is our grid zone designator. A grid zone is very large. It's a 6-degree longitude zone by an 8-degree latitude band. For example, 17R covers all of peninsular Florida and some of southern Georgia. Our grid zone is broken down into 100,000 meter grids, and this map falls into grid November Lima. Now we have magnified our little slice of Earth enough to visualize our grids. This is an easting as USNG runs from west to east. The 0 is our 10,000 meter grid, and the 7 is our 1,000 meter grid. And now we've moved on to our northing because USNG runs from south to north. You can see our 9 is our 10,000 meter grid, and our 2 is our 1,000 meter grid. Now you can see the relevance of expressing our coordinates as easting and northing. We read right and then up, just like coming right up. And that is the strength of grid navigation. With just 4 digits, people operating in the same 100,000 meter grid square can share their position to a 1 kilometer resolution. 0692 puts us into a 1 kilometer grid in this example. So if you want to have 100 meter resolution, add 2 digits. And please excuse my artwork in this example, but this shows us the location of 087953. If you need a 10 meter resolution, add 2 more digits, such as 08759535. It is much more practical than loud and long. The 6 digits to give you 100 meter resolution should be sufficient for most tasks. Now let's bring our discussion of grid into further relevance. Our baseplate compass not only has inch and millimeter scales on the sides of the compass baseplate, it also has a couple of grid tools useful for 2 of the most popular gridded map scales, 1 to 25,000 and 1 to 50,000. Now you can see the grid tool in use, obtaining the grid coordinates of a trail intersection at 076947. The grid tool is only used for the last digit of our easting, 6, and our northing, 7. The rest of the work is done solely by using the grids on the map. After you do this a few times, you can plot the 100 meter point fairly accurately without a tool. We're going to start our exercise at this time. The first place we will mark is our current location, which is going to be at this intersection right here. Notice that I use a pencil because pencils do not run out of ink, can be sharpened with crude methods, they can be erased, and the eraser is a good way to clean exposed electrical contacts. They can write when frozen or wet and can be used for fire starting if need be. We mark our location with a circle as we are using our intersection as a point for plotting our bearings, and writing large solid dots can obfuscate details on the map. When marking our points on the map from our grid coordinates, we will make small marks. This is coming from my mechanical drawing classes 40 years ago. Small marks, big precision. If desired, we can circle our points as we did for our point of origin. Okay, we've received our first coordinate, 090954. So we go east first to 09, and then we go north to 95, and that puts us in the ballpark right there. So now we'll take our grid tool and lay our grid tool up on here and bring it to 4. And then you can look underneath our little box right here, and you can see that this is where we need to make our point, and our point is right at this intersection. And again, if you want to make a circle around it, you can certainly do so. Let's do our second coordinate, 062937. 0693. Now take our grid tool, 06 to 2, then bring ourselves up to 7, and look in our little box, and we can see that we are just above this small feature here. Next, 085939. 0893. So 939, and that's going to be 5. So we're at 5, and we're at 9, and that's where our mark is. Looks like we're just south of this pond right here. And if you desire, you can certainly check your marks again to make sure you're squared away. And in reviewing everything with our grid tool, we can see that we made a boo-boo in this mark right here, so we need to bring it back in about 45 degrees to bring us squarely in the box to make that correct. And what's nice is again, you can erase marks with a pencil. Much better. Now we need to orient our map north. So take your compass and make sure that you're aligned north and south. And from this perspective here, it's easier for me to use my back bearing mark and line up south. What we'll do is line up the edge of your base plate compass along a grid line. And you can confirm that also by looking at your grid lines here, and you can see how they're evenly spaced in there. So we're good as far as that goes. Now, since we got this nice work surface we're working on, just go ahead and rotate your compass and box your needle north. Well, now that we've got our compass and map aligned north, we can go ahead and start shooting bearings. And you can see that I've taken advantage of this work surface and I've secured the map to my surface. Again, for mechanical drawing, move your tools, not your work. Okay, let's shoot our first bearing. This is where we're starting. This is where we want to go. Direction of travel. Line up on our intersection, then line up at our point. Box your needle. And it looks like 60 degrees. And what's curious, when you're using one of these reduced bearing compasses, that your back bearing and your forward bearing are going to be the same numerical value. It's just going to be in opposite quadrants. Also, this is in our northeast quadrant. So right here, that's the Goldilocks zone. And remember, we don't have to do any kind of changes or any kind of math. So that's also going to be 60 degrees whole circle bearing. Okay, let's shoot our second bearing. Line up in our direction of travel. And it looks like that could be a back bearing for our original one. Box our needle. Check our alignment. And it looks like we are 62 degrees southwest. Okay, let's shoot our last bearing. Again, paying attention to our direction of travel. Lining up between our points. Boxing our needle. Confirming alignment. "36 degrees southeast." Let's discuss our calculations as it relates to the quadrant bearings we took and the conversion to full circle bearings. You know, honestly, the only time you would really need to do a conversion like this is if you were interoperating with others who are using a full circle bearing compass. And it's clear navigation is possible if working alone with a quadrant bearing compass. Our first bearing is 60 degrees, is in the northeast quadrant, which is the Goldilocks zone. We don't have to do any conversion at all, so it's 60 degrees whole circle bearing. Our second bearing is 62 degrees southwest, which southwest is going to be clockwise, so we add 180 degrees. And that gives us 242 degrees full circle bearing. Our next is 36 degrees southeast, and southeast is going to be counterclockwise. So we subtract 180, and that gives us 144 degrees whole circle bearing. It's good to know how to do this because it's going to allow you to operate a quadrant bearing compass in a full circle environment. However, to round out this capability, we really need to know how to convert a full circle bearing given to us to a quadrant bearing, and it's just as simple. Now, in the circumstance where someone has given us a whole circle bearing and we need to convert it to quadrant bearing, we use subtraction to solve each one of these conversions. The only difference is we subtract our given whole circle bearing from our quadrant bearing reference. In the counterclockwise oriented quadrants of the southeast and the northwest, whereas we subtract our quadrant bearing reference from our given bearing in the southwest, which is clockwise oriented. You can see in our examples here how this sorts itself out. You can look at the first example, and we have a given bearing of 285 degrees. We subtract 285 from 360, and we get our quadrant bearing of 75 degrees northwest. In our second example, we are given a bearing of 237 degrees. And to solve this, we just flip our subtraction order, subtracting 180, which is our quadrant bearing reference, from our given bearing, giving us a quadrant bearing of 57 degrees southwest. In the third example is solved just like the first. What's cool about SAR topo is that you can go back after the fact, plot the points on the map in the program, and then check how accurately you plotted your bearings and points on your paper map. And that is what we have done here. Keep in mind that as much as 1 degree variation in this program depending on the angle of the line between the 2 points measured. In point 1, you can see I was off by 2 degrees. And you can see in point 2, I was also off by 2 degrees. On point 3, I dropped the ball and was off by 4 degrees. This demonstrates that it is possible to get decent precision out of basic tools. In this slide, you can see just how large of a distance a 4 degree variation will put you off over a distance of a tad under 1 kilometer. In actual movement over terrain, maintaining a tight bearing is difficult, and we will discuss practical movement over terrain in another video. This is an example of what I'm talking about. You can see from an aerial image layer applied over our base map that trying to apply point-to-point navigation over these positions will be an unpleasant and difficult task. Point 3 would appear to be possible from what we can see here, and this is something to always keep in mind, that a map is not always the most accurate picture, and the value of the observations of the man on the ground are greater than the estimations of those who may be providing direction from a remote location. Again, we will discuss movement over terrain in another video because the basics we cover here give us basic tool awareness only. Ask me how I know. Someone who's been hopelessly lost, sometimes overnight on several occasions before smartphones and GPS, and forced my way through ridiculous terrain features because I didn't know any better and was too proud to admit it. I've learned the value of knowing one's limitations, the value of planning, the value of training, and just slowing down a bit to make sure you're going the right way before commitment to a course of action. So dust off your compass, make a few maps, and do some exercises that we did today. Involve your friends and coworkers. It actually is a fun pursuit. Well, let's review what we covered. We discussed the anatomy of a baseplate compass and its use. We discussed quadrant bearing and full circle bearing and how to make them interoperate with one another. We discussed US National Grid, including an overview of grid navigation, and also the use of simple grid tools that are part of a baseplate compass. We had an awareness level discussion of SAR topo so you can generate your own maps to practice these skills on your own. Then we pulled everything together in a final exercise and conducted a hot wash where we evaluated our exercise. And we did it all in less than a half an hour. Expect more land navigation content in the future. I hope this helps. This is Brett from SurvivalComms. Till next time.